All right. So for this video, we're going to talk about energy, which is a pretty broad term. There's a lot of different directions we could go with that. But we're going to start out here. There's two main types. Two main types of energy. You've got kinetic energy, and you've got potential energy. So all energy is really going to be classified under one of those two types. So kinetic energy is going to be energy that's based on, we're going to say based on movement. Okay? So if I'm running, I have kinetic energy. If I throw a ball, the ball now has kinetic energy because it's moving. Heat is actually kinetic energy because the particles inside something are moving. If I'm falling, that's kinetic energy. Kinetic energy is anything based on movement. Now, potential energy is stored energy. So, stored energy is like if I take a rubber band and I pull it back. That energy is now stored so that if I let go, it'll become kinetic. It'll be released. Or if I'm on top of a cliff, I have potential energy based on how high I am. If I fell, I would then have kinetic energy. So potential energy, basically it's energy that's stored with the potential to become kinetic, if that makes sense. So any type of energy that's out there is going to fall under those two major classifications. There's a lot more types like mechanical, thermal, chemical, gravitational, electrical, things like that. But all those are going to fall into those two main types. So out of all those types I just mentioned, we are going to focus on two of them mainly. So we're going to look at chemical energy first. All right. So chemical energy is, I'm going to switch to typing here, energy stored in the bonds of a compound or molecule. So for example, if we have H2O or C6H12O6, glucose, those chemicals have energy stored within those bonds, within the chemical bonds. There's energy stored. All right. Next question is chemical energy going to be potential or kinetic? Well, there's your key word right there. It's energy stored. So chemical energy is a kind of potential energy. Okay? Chemical energy is a kind of potential energy. So we're gonna learn more about that in a minute, but now let's look at thermal energy. Thermal energy is energy based on the movement of atoms within a substance. So everything is made up of atoms, right? Living things, non-living things, everything is made up of atoms. And these atoms are always vibrating, sometimes faster, sometimes slower, but they're always moving around, vibrating back and forth, even if something's a solid. If you look at something and it's solid and it's sitting still, like this water bottle I currently have right in front of me that you can't see, but I can, it looks like it's still, but really the atoms inside it are vibrating back and forth. So this is a kind of energy, thermal energy. Is it kinetic or potential? Well, again, there's your keyword. Movement is going to be kinetic. That's a type of kinetic energy. And thermal energy might look familiar. Thermal energy can be transferred as heat. Thermal energy can be transferred as heat. So if something has more thermal energy, it's going to feel hotter if you touch it. That means its atoms are moving back and forth faster. That way, as you heat up a gas, the atoms are going to move back and forth a lot faster. And that's why it feels hotter. So, basically thermal energy is just how fast the atoms are moving within something. Alright, so, we've talked before about the law of conservation of mass. Now we're going to talk about the law of conservation of energy. Equally important. Also a law that you cannot break. Okay, what it says is energy cannot be created or destroyed. So energy doesn't appear out of nowhere, disappear out of nowhere, just like atoms don't. It can't be created or destroyed. It never goes away. However, can't spell today, it can be transformed. So this is the key part here. It can't be created or destroyed, but it can be transformed. Alright, and that's what we're going to focus on a little bit today. So let me leave this up here. It can be created or destroyed, but it can be transformed. So let's look at a few examples. And by transformed, I mean, like the rubber band example is a simple one. I pull it back, I have potential, I let it go, it becomes kinetic. If I put a ball on top of a cliff, it's got potential energy. If it rolls off, it starts falling, it's moving, that's kinetic. A roller coaster is another easy one. But those are all physics examples based on motion. We're trying to focus on chemistry. So we're going to talk about how chemical energy can be transformed to different types. So if you have chemical energy, you can transform it to mechanical. Okay? You can transform it to let's see, you could transform it to electrical. Okay? You can even transform it to radiant energy. And by radiant, I mean light. So, chemical to mechanical. What's an example here? How does that work? Well, let's say I eat some food. Within that food, there are different things. For example, sugars. If I eat something that has sugars inside of it, my body takes those sugars and breaks them down into the different molecules that I need, the different nutrients. So I'm taking those potential energy stored within the bonds of what I eat and breaking it down. ATP, glycolysis, all that good stuff that you hopefully learned in biology. Now, where that comes in handy for us is we need to do things. We need to move around. We need to be able to think. Things like that. We need energy within our bodies. So what we're doing is we're taking chemical energy and converting it to mechanical. So I'm going to write food is an easy example here. Okay, we eat food. That's what we need. All right. Another example is chemical to electrical. All right. How we're going to do this is batteries. Okay, batteries work by a chemical reaction. We talked earlier this unit about redox. Well, turns out batteries are just one big redox reaction going over and over. Okay, electrons flowing around. Cations and anions, all that stuff. We're going to learn more about how that works a little bit later on. But just know that batteries are based on chemical reactions where you convert chemical energy to electrical. Okay. Next one is radiant energy. Fireflies is a good example. That's an example you see naturally. So, fireflies, they produce light. I'm sure you've seen this before. They light up. So, the way that works is it's a chemical reaction going on inside the firefly, or lightning bug, or whatever you want to call it. The chemical reaction does something called chemiluminescence, which just means it's a chemical reaction that produces light. It's just converting that chemical energy into radiant energy through transformation of energy. So, the last one I want to talk about is chemical energy to thermal energy, or heat. How does this happen? Well, when you do a chemical reaction, in order for the reaction to happen, you have to break the bonds of the reactants in order to form the products, right? Well, when you break these bonds, when you break the bonds of the reactants, energy is transferred from chemical energy to thermal energy. That's another example of potential to kinetic. Chemical energy to thermal energy. So, anytime a chemical reaction occurs, let me write this down. Anytime a chemical reaction occurs, energy is gained or lost by the system. Alright, and when I say system, let's say we have some chemical reaction going on in the beaker here. We mix some blue stuff with some red stuff. Let's say it's acid-base. Okay? Your system is literally just the reactants and products. Okay? Put quotes here. Your system is literally, in chemistry, it's just the chemicals that are reacting, just the reactions and products. Everything else, the beaker here, the air here, this is what you call the surroundings, or the environment. Alright? So the system is just the reactants and products, the surroundings is everything around it, including the beaker. Okay? So, anytime a chemical reaction happens, you're going to either gain or lose energy. So, there's a couple examples of these reactions. Alright? One kind is, let's say we have methane gas, and we burn it. Alright? As we learned before, it's just going to make carbon dioxide and water. Okay? This is what you call exothermic reaction. Okay? So what you call an exothermic reaction. An exothermic reaction is something that releases energy. Okay? So this particular reaction, it's burning. Okay, you can see the energy release. You can feel it. You can see the light energy being put out. You can feel the heat being released. So exothermic reactions is a reaction that releases energy. Okay. Another reaction that you might see is so the opposite, and I'm not gonna write this one down for the sake of time, but if you mix ammonium nitrate and water, you're going to get what you call an endothermic reaction. Okay? In an endothermic reaction, the system is actually going to absorb energy. So with the exothermic, you see fire, you see heat and light. That's clearly energy being released. So if that beaker we had up here earlier, if you do an exothermic reaction while you're holding this beaker, you're going to feel the beaker get warm. That energy is being released. The beaker is going to take it in and the beaker is going to feel hot. Alright? If you do an endothermic reaction and you're holding the beaker, you're going to feel the beaker get cold because the reaction is going to take heat energy out of the beaker in order to fuel the reaction. Okay? So endothermic reactions absorb energy, exothermic reactions release energy. Okay? Pretty simple there. And it's kind of nice that you have some STEM words there. Okay? Therm for heat or energy, exo for out. So you could think heat exits, exothermic. Okay? Endothermic, heat in, endothermic, heat in. So pretty easy to remember. So another nice way to do this is you can actually represent it graphically. So I'm going to do a graph here. Okay, this is just going to be the reaction energy graph. So the bottom we're going to have reaction progress, which is basically just like the time. And on the side, we're going to have something called H, which stands for enthalpy. Okay? Now, let me move this down just a bit here. So enthalpy is basically the heat content of the system. So we're going to draw a graph to measure how much heat energy is in the system, right? Or how much energy is in there. Now, the thing is that we can't measure how much heat is in the system, so we really look at change in enthalpy. Okay, which is just the change in the heat content of the system. And we write, whereas we write enthalpy as H, we write change in enthalpy as delta H. You're going to see this a lot in upper level math and science classes. Delta just means change, and that triangle is delta. So that is your change in enthalpy. So back to our graph. All right. So you're going to see something a lot of times like that. That's what these reaction energy graphs are generally going to look like. So let's go ahead and label a few things to try to make sense of this. All right. If this is basically time down here at the bottom and down here, then where are the reactants going to be, at the beginning or the end? All right. Obviously, the reactants are going to be here, where we start out with. Then it makes sense that the products are going to be what we end up with. Okay, so there's your reactants, there's your products, what you start and end with. Okay. Now, the energy, this line here represents the energy, the heat energy within the system. Okay? So, if this is the energy that we started with here, and this is the energy that we ended with here, then we can say that the change in energy, our delta H, is just this difference, right? So the difference between here, okay, and here. That's our delta H. Difference between the energy of our reactants and the energy of our products. Okay? So in this particular reaction, did we lose energy or gain energy? Alright? So our reactants are up here, the reaction happens, and our products appear to have less energy, going by a graph. So that means this reaction lost heat, which means it's got to be exothermic since it released energy. Okay? And delta H is going to be negative. So we have a negative delta H. Okay? Our change in energy was negative since we lost energy. Okay, so let's look at another graph here. All right. So that was an exothermic reaction. Let's try to draw an endothermic reaction now. If you want to try it yourself, go ahead and pause it and give it a shot. If not, you can watch me and go through it. So here's our reactants. Okay, our reaction happens. And we've got our products. So let me label my axes here so we can make sense of this. So there's our reaction progress. There's our enthalpy. Alright. So here's our reactants. Here are our products. And we're going to be looking at the difference. So our delta H here is going to be, here's where we started. Here's where we ended. That is our change in energy. So we can say delta H is a positive delta H. It's endothermic. We say it's endothermic because we have more energy at the end than we did at the beginning. So that means it absorbed energy. And we say it gained heat or gained energy. So if you're holding the beaker is going to be cold, but the actual system had to take energy in. Okay? So one more thing I want you to notice about this particular reaction, by this graph, is as this reaction energy progress goes, here we have reactants, but also we have this big peak here before we end up in our product. Okay, that peak actually represents the chemical reaction. All right, so that peak actually represents something called, okay, we abbreviate it as AE, but something called activation energy. So let's head back up there and look. Activation energy is basically just the energy that you need to activate the reaction, to begin it. So if we're going along here, in order to do the reaction, we have to get enough energy to get over this hump, to get back down to the products. If you don't have the activation energy, the reaction won't happen. Okay, so that's just the energy needed to do the reaction. So that also means this part in between reactants and products here, this is what we call our transition state. Transition state. So transition state is literally just during the reaction. It's what you have in between reactants and products. Okay? Sometimes it lasts longer, sometimes it lasts shorter. It just depends on how fast the reaction goes. So, one more thing I want to go over before we do a couple practice examples. Let's clean it up a little bit. I'm going to go ahead and draw reaction progress. I'm getting lazy with my abbreviations here. Enthalpy. So let's do another exothermic reaction. Okay? So we've got our reactants, our products, we've got our delta H here, and we've got our activation energy there. Okay, so this reaction's got a pretty high activation energy, which means it's kind of tough to get it to happen. You need a lot of energy. This reaction is one that takes a really long time. So there's something called a catalyst, which is something that its job is just to speed up a reaction. Okay? It's not a reactant, it's not a product, it's just something you can add in that makes the reactants react faster. So, what it's going to do is, you have the same reactants, right? Okay? And you have the same products, the same reaction happens. But it speeds it up. Okay? It speeds it up. So let me write that in before we do it. The catalyst speeds up a reaction and lowers the activation energy. That was great timing. Okay, sorry about that minor interruption. I should have been paying attention. So a catalyst is just basically something that speeds up a reaction and lowers the activation energy. So it kind of lowers that barrier here that it has to get over. So that means if we were to draw the graph for the same reaction with a catalyst, again, we've got the same reactants and the same products, but its pump is not going to be as high. So it's going to look more like that. So that reaction is going to happen a lot faster. Since the activation energy is so much lower, that thing is just going to go. So that's a catalyst's job. It's just going to speed up a reaction and lower the activation energy. An example we saw in class was you have hydrogen peroxide. It's going to decompose into water and oxygen. Okay, this thing is really slow. You know, if you see peroxide in your house in a bottle, it's not, spouting off water and oxygen everywhere and rapidly decomposing. It doesn't work that way. However, if you add manganese dioxide catalyst, okay, that thing's going to go. It's going to put off a lot of oxygen fast, and this is one of the ones we did in the lab. If you do this reaction, you add manganese dioxide to peroxide, and you hold a match over it, it's going to catch on fire because of all the oxygen coming off. So that's an example of where a catalyst makes things go really fast. Okay, you might be saying, who cares? I don't have any manganese dioxide. How does this really apply to me? Well, catalysts are actually playing a very, very, very important role in your life because there's something called enzymes, which are basically just biological catalysts. So you may or may not have learned about these in biology, but enzymes play a huge role in all of the different cycles that go on to give you energy and keep you running. Without catalysts, none of the reactions that are going on inside of you would work. Enzymes have a huge, huge role, so that's really, really important. And one cool thing that's going on in science today is we're trying to create artificial enzymes that do things even better. So that's just something that's really interesting. So just go back and look over the graphs here. Make sure you understand, let me pull this back up. Make sure you understand, if you were to look at one of these graphs, make sure you understand how to label reactants and products, how delta H is the difference between reactants and products, and activation energy is just the energy that you need to get over this hump here. Okay? If you can do that, you're pretty good. And obviously understand the difference in exo and endothermic. So look back through this thing, make sure you got it all, and this is it for the unit. So if you've watched all the videos and you all understand it all, then you're pretty good off.